All right, there we go. Okay, so when we last were together, we were talking about compound nomenclature, and we had started the flow chart for nomenclature. We're going to pick up with that today. I'm going to add a little more to it. What we've talked about so far are the ionic compounds. Ionic compounds have ions. That makes it easy. And that's always going to be something on the left side of the periodic table, right? A metal, which is quite a bit, right? It's the majority of the table. Anything to the left of the metalloid stair step, which we know always lose electrons to become positive ions or called cations, right? And that positive ion is going to partner with a negative anion, which is going to be something to the right of that metalloid stair step. Or it could be the negative ion. It could be one of these nice polyatomic ions. Just to be clear, on Thursday, I said you do have to start memorizing these. You'll need to know them by the first test. They will not be provided. There's a Quizlet for you to help practice. Personally, for me, Quizlet probably wouldn't have helped me. I do better writing things down. So I probably would have made flashcards or written these down on a piece of paper, maybe a few times. I do it much better that way. Okay, so we had talked about when it's an ionic compound, your job is to name the two ions. So you have to name the positive ion, you have to name the negative ion. And that sounds pretty straightforward. The problem is, of course, as we talked about, the metals, there's two different types, right? There's the type 1 metal where we know what the charge is. Lithium is always a +1. Magnesium is always a +2. And then on that diagonal, aluminum, zinc, silver, always 3, 2, 1. So for those type 1 metals, all we do is we just name the metal. And we had also talked about that you only have one polyatomic cation, and that is ammonium. So if that's going to be on the compound, it will appear first because it's positive. And it acts like a type 1 metal in that you just name it. So if you see NH4 at the start, you're just going to say ammonium. The type 2 metals, however, which is our big group of transition metals, of course, except zinc and silver. We know those. These are 2-in-1 type 1 metals. We know the charge. Everything else, though, right? Chromium, cobalt, iron. And don't forget these couple of metals underneath the metalloid stair step that we need to know. SN, which is 10. PB from plumbum, which I always thought plumbing, that's your lead, and then Bi bismuth. These are the three where we'll need to know the name. So you just want to make sure and remember these are also type 2 cations. There's 2 or more possible charges. And when that happens, we have to now include the Roman numeral to indicate the charge on the metal. So there's an additional step with type 2 metals. Then what we practiced was if those metals are partnered with a nonmetal, it's going to be a binary compound. It's only going to be a metal and a nonmetal, so only 2 elements present. And whenever we have that situation, we always push an IDE ending. So if we see fluorine and we just say fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, which we really don't, it doesn't roll off the tongue, right? Nitride, phosphide, carbide, that's if we have just a single nonmetal anion. We just add that IDE ending. The other scenario, though, is that it could be a polyatomic anion. And in that scenario, we're going to name it exactly as we've memorized it. So like if we see NaClO3, we're going to say sodium chlorate. If we see NaClO2, we're going to say sodium chlorite, right? So the ClO2 part we name just as the sheet tells us to. Of course, that sheet's going to be in our memory bank, right, in our head. So it's going to be what our memory tells us to do. So picking up where we left off, right, and polyatomic ions, just to make sure it's clear. I know no one's a big fan of this, but you do want to memorize those. There's a list in my courses. It's the list I just showed you. All right, so just make sure you're starting that for your first test. And so what we're going to do here is just practice what we've sort of talked about last week, and then now looking at polyatomic ions. So first thing is I see K. And I think most everybody at this point, you're like, okay, that's potassium. All right, now I got to go find it on my periodic table. And I know potassium, it's a group 1 alkali metal. I know it's always a +1. That means I don't need the Roman numeral because when you say potassium, already included in that name is +1, right? We know it's always a 1. So you don't have to say potassium 1 because it would be redundant, right? You don't need it. Then everything that follows is the polyatomic ion. All right, so I'm going to highlight it just to make it easier. You pull out the metal, and then everything else that follows is the polyatomic. Now, the hydrogen can get confusing, and this came up as a question, I think, after class on Thursday, so we are going to talk about it today. If I look at my polyatomic ions, I've got CO3 -2, which is carbonate. And when I was trying to give you a way to memorize the polyatomic ions to make it as easy as possible, I'm not saying it's easy, but I'm trying to make it as easy as I can, is that when you add that hydrogen in front, it's still a polyatomic ion, like it still is carrying a charge, we add the word hydrogen. So what you'll notice is you've got CO3 -2, which is carbonate. And then when you put the H in front, the charge has gone up by 1 because hydrogen carries a +1 charge. Now we call it hydrogen carbonate, right? It's still the carbonate, but now there's a hydrogen with it. So hydrogen carbonate, also called bicarbonate. Now, if I do add a second hydrogen, now what's happened is the -2 charge of the carbonate has been balanced by the 2 +1 charges of the hydrogen. So the charge now has gone to 0. At that point, it is no longer a polyatomic ion because it doesn't carry a charge anymore. At this point, it becomes an acid, and we're going to get to acid nomenclature in a little bit. So it's not going to be named dihydrogen carbonate, even though that's exactly what it looks like. Instead, because now we have an acid, we have to do a different nomenclature system. So sometimes that's a little confusing. So if the H is in front, it is an acid. Now this compound, we don't have H in front, we have K. So we know that this is ionic, not an acid. So we start by naming the metal, potassium, and then I'm looking on my polyatomic ion list for HCO3, and that's what we were just looking at. Your choice, you can name it hydrogen carbonate, or you can name it bicarbonate, either one perfectly acceptable. All right, so I'm gonna stick with what I think is like a way to maybe make it easier to memorize. Maybe not, but I think of, okay, here's my carbonate CO3, getting that stuck in my head, right, for the test. Hydrogen, right, so there's my hydrogen, and then potassium in front. So potassium, hydrogen, carbonate. But again, if you gave me potassium bicarbonate, it is just as good. All right, so both of those are the correct answer. All right, next one, I've got Fe, which I know is iron. So now I'm going to go to my periodic table. Oh, and I should mention this too. A lot of times students are like, does capitalization matter? When you're writing the name, then the answer is no. When you're writing the formula, then the answer is yes. Because like if I had done KHCO3, where I made the O lowercase rather than capital, this starts to look like cobalt rather than carbon and oxygen. So when you're writing the formula, yes, capitalization matters. When you're writing the name, that doesn't matter to me. All right, so potassium hydrogen carbonate, this is Fe, iron. Now, when I go to my periodic table, iron is one of those type 2s. I don't know the charge of iron, and that's because in different compounds, it is a different charge. So I have to figure it out based on what it's partnered with. So we pull out the metal, and then everything else here is the polyatomic. So I'm going to go and look at my list of polyatomic ions and find PO4. All right, not PO3, but PO4. You have to always be very careful about the number of oxygens. So when I look at my list, PO4, -3 charge, phosphate. So I'm going to write myself a little note. All right, PO4, -3 is called phosphate. All right, the reason why that's important is I not only need to say, okay, PO4 is phosphate, but I also need to figure out the charge on the iron and use that Roman numeral to say, okay, this is the charge on the iron, right? So that Roman numeral is going to come from understanding the charge balance here. So the PO4 group, the phosphorus with the 4 oxygens, together as a group carry 3 extra electrons. So this entire highlighted group is a -3 charge. There's only one of them in the compound, right? There's just that one PO4 group, -3 charge. And there's only one iron here. So to balance, that iron has to be a +3 charge. So my Roman numeral here is going to be iron 3 phosphate. So always remember the charge on the metal is the charge that we put for the Roman numeral, right? That's the number we want, not how many irons we have, but what's the charge. So we say iron 3. All right, if we do the next one, this one looks like it would be a lot. right? I mean, it kind of is, but not really. There's still only two pieces. It doesn't look like it, but it is. First piece is always the metal, or ammonium, NH4 if you had that, but we don't have that here. So we look at the metal. Mg, we know magnesium. All right, then I go to my periodic table. I find magnesium. It's a group 2 alkaline earth metal. And so I know that that means the charge is always +2. All right, and so that means I don't need a Roman numeral here because it would be redundant. Now that thing in parentheses, right, that is my polyatomic ion. And if I look, again, I got to be careful here. There's HPO4, all right, but we want H2PO4. So PO4, like we saw up here, is phosphate. So it's going to kind of make sense when I look at my list here that H2PO4 is called dihydrogen for 2 phosphate, right? There's my PO4 phosphate. There's the 2 hydrogens. So dihydrogen phosphate. All right, so magnesium, dihydrogen phosphate. All right. Now, again, kind of like we were talking about with the carbonate, the phosphate PO4, -3, right? Polyatomic. That is sort of the base polyatomic ion that I want you to make sure you have memorized. Remember all the 8s. So I know phosphate, PO4 -3. Then I know that PO3 -3 is phosphite. We talked about 1 less oxygen changes 8 to 8. So phosphate, phosphite. Charge is the same. We just dropped an oxygen. Then if I know that adding a hydrogen to phosphate, right? Oops. And it's supposed to be charge of -2. Okay. I was looking at the number and my brain was going in 2 different directions. So here's phosphate, -3. When I add a hydrogen, charge goes up by 1. So now it's -2. Still a polyatomic ion, hydrogen, phosphate. If I add another hydrogen, charge goes up by 1. So now this is dihydrogen phosphate. If I add one more hydrogen, H3PO4, the charge has now gone to 0. So it's no longer a polyatomic ion. So this is not trihydrogen phosphate. It's going to be something called phosphoric acid, but we're going to get there later. We're not there yet. All right. So now let's go in the opposite direction. With ionic compounds, the charge has to balance and go to 0. Compounds like atoms are always neutral. So ammonium, I know, is the name for NH4 +1, all right, because that's from my list of polyatomics. And this one here, normally ionic compounds start with a metal, and we know this doesn't sound like a metal, right? There's no element named ammonium. So that's sort of your cue that it's a polyatomic. So ammonium, NH4+. Carbonate, like we were looking at earlier, is CO3 -2. So again, when you do ionic compounds, you're naming the 2 pieces. So ammonium names the NH4+, carbonate the CO3 -2. Now again, charges always have to go to 0 overall, kind of like atoms. They're always neutral. Compounds are always neutral. So if carbonate is a -2, I need to have a +2. Since ammonium is just a +1, I'm going to need 2 of those, right? Because now +1 is +2 overall, total. That'll balance my -2. So when I write this, because ammonium is a group, it's not just a singular like magnesium, right? I'm going to put parentheses around the polyatomic, NH4, follow it with the 2, and then I'm going to put the carbonate. So I need the ammonium times 2, right? We needed 2 of them with the carbonate. Now, sometimes, not often, but sometimes I'll have students say, okay, well, can I just do N2H8CO3? And the answer is no. If you do that, it's hard to recognize that that's still ammonium, right? So you don't want to distribute. You just want to put the parentheses and then the subscript. Now, the other thing we talked about in the last video is that you're just doing a crisscross here to balance the charges, right? So we talked about how the charge on the anion becomes the subscript for the cation, absolute value, right? And the charge on the cation becomes the subscript for the anion. Now, there's no 1 written in here, but we know it's a 1, right? Technically, the carbonate has a subscript of 1. So charge of anion, subscript for cation, charge of cation, subscript for anion. There's a little crisscross, right? If we try the next one, we've got calcium, Ca, which is a group 2 alkaline earth metal, just like magnesium. So we know it is always a +2 charge. So there's my first part, right? That's why we don't need the Roman numeral, because we can get it just by looking at the table. Now, the hypochlorite, if you remember, there were 4 possibilities with the halogens. You could either have 1 oxygen, 2 oxygens, 3, or 4. The lower the number of oxygens, you get the ite ending, and the fewest is when we add the hypo, right? So what I had told you on Thursday was memorize the chlorate, then you know 1 less oxygen is the chlorite. And if I go even 1 less oxygen, we borrow from biology, hypo and hyper, right? Except it's per rather than hyper. But hypo meaning very low in oxygen. So this is lowest, right? So ClO, right, is -1. So hypochlorite is ClO -1. All right. Now, again, my charges don't balance here. So if calcium is a +2, I'm going to need a -2 to balance. So I'm going to need 2 hypochlorites. So on this one, you got to be really careful. Sometimes students are going to give me CaClO2, right? And they forgot the parentheses. And this isn't right, because this actually looks like calcium chlorite, but then the charges don't balance. So that doesn't work. Anytime you have a polyatomic ion and you have to have more than one, like we did with the ammonium, you've got to make sure and include the parentheses. So now we can see that this is calcium with hypochlorite balancing the charges, because calcium is a +2, that 2 subscript goes on the hypochlorite. All right, just crisscrossing charges there. Okay, last one here, we got chromium 3. Chromium we know is Cr. All right, that Roman numeral 3 is telling me it's a +3 charge. All right, then sulfate. Remember, the last 3 letters are so important, because on our list, our possibilities, right? We can have sulfide, right? If it's sulfide, we know it's just S, right? We talked about binary compounds, IDE ending, so just a nonmetal. But I see 8 here. So there's 2 possibilities. We have SO4 -2 and SO3 -2, right? The 8 is the more oxygens. So SO4 is sulfate, SO3 is sulfite. All right, so SO4 -2 is the anion here. Sulfate SO4 -2. All right, now, if you want to do this, what I think of as the long way, it's not really, you just find the least common multiple between the 2 charges. So between a 3 and a 2, it'd be a 6. So to get a +6 from chromium, we would need 2 of them. All right, that would give me my +6 overall. And then for the anion with the sulfate as a -2, to get to a -6 to cancel out the charges, I would need 3 of those. All right, so that would be my charge balance. 2 chromium +3s to get a +6 total, 3 sulfate -2s to give me a -6 total. So I'm going to write Cr subscript of 2 because I need 2 of them. And then parentheses around the polyatomic ion sulfate multiplied by 3 because I needed 3 of them. But remember that crisscross makes this really easy. The charge on the chromium became the subscript on the sulfate. The charge on the sulfate, absolute value, became the charge on the chromium. So there's always this little crisscross thing that makes it nice and quick. All right, you don't have to go through what you might consider the long way, which is finding the least common multiple. Okay, now hydrates are something we're going to look at in lab. So we want to make sure we know how to name these. It's really easy. All you do is it's going to be an ionic compound that has water molecules trapped inside the crystal structure. So they're called hydrate, right? Because they're not wet, but technically they're wet. There's water molecules in that. They have like little box structures, and the little water molecules like to get into the cubic structures. So if I see MgSO4 dot 7H2O, that would still be Mg magnesium, SO4 like we just saw sulfate. So you name this just as you would. And then the hydrate is referring to the water. And we just name the number of waters using the correct prefix. And for 7, it's heptahydrate. Now the prefixes, if I go back to that list of polyatomic ions, down at the bottom, These are your 10 prefixes that you also need to memorize. Most of them are really simple. Mono, di, I've never had students confuse those. Same with tri, right? 3 for triangle, tricycle, that all makes sense. 4 for tetra, tetrahedral might be familiar. I remember when I was in, first learning this, I thought of Tetris, which may not be a game anybody knows anymore, but a lot of four-sided structures. So I thought, okay, Tetris 4. I don't know. Anyway, tetrahedral. Penta is for 5. Pentagon, that might be familiar. Hexa, remember the X for 6. So 6 means hexa. Hepta, 7. Can't really help you too much there. I think in Spanish it's septa, but that's probably not that super helpful. 8, octagon or octopus. So that makes sense. Octa. 9 made sense to me because it looks like the double N. It just looks like it would be 9. So nona. And then deca, like decade. So those are the 10 prefixes. There are others, right? You can keep going. Like 11 becomes undeca, 12 becomes dodeca, but we're going to stop at 10. And we usually don't even go up to 10 anyway. Okay, so that's why this one was hepta, hydrate, hepta meaning 7. All right, so if I was just going to do one more here, let's say we had Na2CO3 dot 2H2O. All right, so if I'm going to name this, all right, Na, sodium, don't need a Roman numeral, right? And then we know the CO3, we saw this earlier, that was carbonate. All right, so sodium carbonate. Then I need to say there's 2 waters. So I'm going to say di for 2 and hydrate for water. So sodium carbonate dihydrate. All right, that's hydrated salts. So, and you'll know it's a hydrate because the water will be there. On the quiz, when it's asking you to do this, when you enter it in, don't worry about the dot. More than likely, the way you enter it in, the system's not going to like it. I'll just go back and fix it. So really don't stress about it. If you're doing the practice test too, I'll look them over. Anytime you have to type something in on the quiz, know that I'm going to be looking it over. All right, now the next part we have to go to is we're going to go back to that flow chart we were making last week. We had started it, and we're going to start talking about the middle. So what we've done so far is we've looked at ionic compounds. And again, our job is to name the 2 pieces, the cation and the anion. When we get to where the compound starts with a nonmetal, which if you can imagine, it's not going to be much, right? So there's only starting with elements on the right side of the metalloid stair step. Now, we're only looking at binary. So it's only going to be a nonmetal with a nonmetal. That's it. One of each. Well, sorry, not one of each, but no polyatomic ions here, right? Because it's not ionic. So it'll be something like NF3 or SO2. It's just 2 elements over here, or like CO2, something that's very familiar. When you start getting like non-binary covalent compounds, it goes into organic chem, usually carbon-based, and then you have a whole new naming system then. So organic chem, you have a different nomenclature system. Okay, so covalent. What's going to happen here is you're going to have nonmetal partnered with nonmetal. All right, now, if you're sort of noticing the flow chart, you're going to say, okay, well, I know what happens if it starts with a metal. I know what happens if it starts with a nonmetal. It'll be covalent. What about a metalloid? Where do those come in? And the answer is it depends. And I know that's a terrible answer. And it depends on something called electronegativity values, which we don't teach until chapter 9 or 8. I think it's 9. Anyway, we don't know it yet. So how do you do that? So for now, what I'm going to say is if there's a metalloid, we're going to put it in this category. So if it starts with a nonmetal or a metalloid, we're going to treat it like a covalent compound. It's an oversimplification, but for now, it's going to work. There are times, though, when the metalloid is in front that it actually acts as an ionic compound, and the metalloid would be a type 2, where we'd have to identify the charge. But again, it depends on what it's partnered with. So for me, on my quiz questions and my test questions, metalloid in front, we're going to name it this way because this is the easier way. The covalent way is always the easier way. But in TRO with the dynamic study guide, there may be a situation, and I can show you where here in just, I'll show you the example, where it's going to show up like an ionic compound. All right, but first, let me give you the rules. When you have a nonmetal and nonmetal, or a metalloid and metalloid, right? Again, you only have two pieces. So you've got your first nonmetal and you got your second nonmetal. So here's the rules. For the first nonmetal, you name it as is. All right. And you add a prefix, but only if there's more than one. Okay. So that's for the first nonmetal. The second nonmetal, because these are going to be binary compounds, there's only going to be two elements present. We're going to do the same thing that we did with the ionic compounds, and that is we're going to push that IDE ending on the second nonmetal, okay? And always use a prefix. Okay, so there's a little inconsistency here, and you have to be a little careful because it's really easy to forget sometimes that you always have to have the prefix for the second nonmetal, no matter what. The easiest example that I can come up with, because everybody's familiar with this, is if we have CO2, we know that that's carbon dioxide, right? Since they start teaching you about plants, which I swear is like every year in science when you're in middle school and elementary school, it's always about plants. And then it doesn't get interesting until high school. So CO2, carbon, name the first element as is. Only use a prefix if there's more than one. There's only one, so we don't use a prefix. We just say carbon. Then the second nonmetal, always a prefix. So dioxide. So two oxygens, dioxide, and again, we push the IDE ending. If I have CO, right, the more toxic cousin, then this is going to be carbon, monoxide, or monoxide. So again, we use that prefix, even though there's only one, but we didn't do that for the first nonmetal, right? We didn't say monocarbon, we just said carbon. So this one, it's really easy to think carbon oxide, but it's carbon monoxide and CO2 carbon dioxide. All right, so that's our next system to learn. This one's usually really easy. In fact, I remember as a student when I would get these on a test, I'd be like, oh, good, this is the easy one. You don't have to memorize anything. You just have to know those prefixes. Again, we're only working with the first 10, but I did put a couple more in there. So we have a molecular formula and name a compound for which contains 2 nitrogen atoms, so N2, and 4 fluorine, so F4. All right, so N2F4 would be the structure. Now let's name it. So again, the difference here is because now we're starting with a nonmetal. All right, so there's no longer ions present. When it starts with a nonmetal, what happens is you have two things that want to gain electrons. So nobody's going to give it up. Instead, they share. And so that's why it's covalent. Covalent means that the electrons are being shared rather than transferred. So if you start thinking about charges here, it's going to get confusing. You're going to say, well, how does that work? Because nitrogen's -3, fluorine's -1. There are no charges here because it's covalent. All right, so back up in here, but the molecular compounds, right? These are not ionic. So I'm just going to write this over here. There are no ions in these compounds, which means there are no charges to balance, which makes these really easy. You know, you just have to know what your prefixes mean. All right, so if it's molecular, right, that's what we're looking for. We're going to have nonmetal with nonmetal. All right, so when I go to name N2O4, first nonmetal, we name as is, nitrogen, and we use a prefix if there's more than one, which there is. So di for 2, so we're going to say dinitrogen. Then the second nonmetal, always use a prefix and push the "ide" ending. So 4 fluorines means I need to say tetra, and fluorine becomes fluoride. So dinitrogen tetrafluoride. Next example, we want the formula for tetraphosphorus decasulfide. So tetra, right, that means 4. Phosphorus is P. Deca, like decade, means 10. And sulfide means sulfur. So now we just got to switch the order because the prefix becomes the subscript. So P4 and then S10. All right, now I know we talked about anionic compounds. simplifying ratios if you can. Like, do I leave this as P4S10 or do I change it to P2S5? And the answer is you leave it, because if this says tetra, then you leave it as 4. So don't simplify when it's covalent. The difference is in ionic compounds, you always want the simplest way to balance out the charges. So if you can simplify a 2-to-4 ratio down to 1-to-2, you go ahead and do it. But in a covalent compound, that's not true. You're not simplifying charges because there are no charges. So tetra stays 4, deca stays 10. All right. Then the next one, we have S7. So we saw this earlier. 7 is hepta. Now notice in the first compound, sulfur was named sulfide because it came second. But because sulfur is first here, we leave it as sulfur. It's only the second nonmetal that gets the IDE ending. So we have heptasulfur, 7 sulfurs, and then 2 oxygens, so dioxide, right? The second nonmetal gets the IDE ending, heptasulfur dioxide, okay? So that's our second system. All right, and what I mean by that is when you look at the nomenclature flowchart, there's 3 systems. System 1, ionic compounds. System 2, covalent, which we just did. These are the easiest ones. I thought these are my favorite, but there's not a lot of them, unfortunately, until you get to organic, and then you get a whole new system. And then we have one more system here, and that's what if hydrogen comes first. So hydrogen is special. It gets its own nomenclature system. And when it has hydrogen first in the compound, it is an acid. All right, H in front. All right, so I'm going to go back to the chart because I like having everything on one page if I can, because then I think I have a slightly photographic memory. I don't have a great memory anymore. It starts to deteriorate when you get to my age. But if I can see everything on a sheet of paper, I'm more likely to remember it. So if you have hydrogen in front, we have an acid. These are still ionic. Okay, so we still have to worry about charge balance here. They're just a special type of ionic compounds. So you still have the 2 pieces, like you're going to have your cation and you're going to have your anion. What's special though is that the cation is always going to be H+. So that makes this a little bit, I wouldn't say easier actually. The rules here are interesting. So the definition though is that your cation in front for an acid is always H. Your anion, like we had with ionic compounds over here, you've got the same 2 possibilities. It can either be a nonmetal or it can be a polyatomic. All right, now that means that we're going to have two different ways of doing this. There's one way to do it when you have a hydrogen with a nonmetal. There's another way to do it when you have hydrogen with a polyatomic. Okay, so let's look at the first one. All right, so first one is called a binary acid. And that means you have hydrogen and a nonmetal. So there's only going to be 2 elements present. That's why it's binary, right? It's going to be hydrogen with like chlorine, or hydrogen with bromine, or hydrogen with sulfur. There's only 2 elements present. In a binary acid, you use a very specific name. You use hydro, leave a space for the root of the nonmetal, and then ic, and then you add the word acid. So you'll see names like hydrochloric acid for HCl, hydrobromic acid for HBr, hydrosulfuric acid for H2S. All right, but the hydro means that it's binary. That's the big thing that you got to remember is when you see that hydro in front, it means that it's binary. That means hydrogen is partnered with just a nonmetal, no polyatomic ion, just the nonmetal. The second type of acid is when it's non-binary, right? And this obviously is when there's hydrogen with a polyatomic. I always felt like these were named backwards. You know, normally you name the cation first and the anion second. Acids are kind of opposite because really the hydrogen's first, but you name it second with the word acid. And if it's a nonmetal, that really is being named first with the hydrochloric or hydrobromic, whatever it is. Same thing's going to happen here, which I know seems a little strange. Your polyatomic ion, remember the endings are either ate or ite. And what we do is in the acid form, we're going to change the name of the polyatomic ion. Ate is going to go to ick, and ite is going to go to us. So I remember doing the data dump on my test, writing that down really quick. I remembered it alphabetically, A before I before O. In hindsight, I'm like, I think it's simpler to just say the I's don't go together, right? Ate goes to ick, ite goes to us. One little mnemonic I used to always say is like, I ate more whatever, ice cream, and it made me sick. So remember how ate referred to the more oxygens? So like sulfate, SO4, more oxygen, sulfite, SO3. So ate is always the more oxygen, and then it turns into ick in the acid form. So I don't know if that helps or not. And then the hydrogen we add with the word acid. All right, so we're going to look at examples of this. All right, but this is the key, is that now that we have a polyatomic ion, we're looking at the endings, and the endings are going to change. Now, the other thing that's really key about this is when you have a non-binary acid, do not use hydro in front. All right, remember the hydro in front is only when you have a nonmetal. With a polyatomic ion, we don't want to use the hydro because then that would be confusing. All right, and then I see something in the chat I just noticed. I ate something icky. That also works. Oh, and Sprite is delicious. Okay, that also works. Sprite, ITE, is delicious. OUS. Okay, thank you. Those are also really good. Okay, so back in the notes, this is the completion of the flow chart. So we've talked about everything so far. We added to that today the covalent compounds, nonmetal and nonmetal. Prefixes are your friend. And then we talked about acids. We got to do some examples here. So again, the big thing to remember is if it's binary, just hydrogen and a nonmetal, there's only two elements in the acid. Hydrogen's always first if it's an acid. It's a very specific name, hydroic acid. All right, we'll practice that. When it's non-binary, don't use hydro, because hydro we always use for binary. Instead here, you name your polyatomic ion first, changing the ending. Ate to ick, ite to us, Sprite is delicious, and then you add the word acid for the hydrogen, okay? So examples, and all of that here is written in the notes. If you prefer to read it or you need to catch it again, it's all right here. There's some examples, but I like everything on a flow chart. So we're gonna practice now some compounds. All right, so first one, we've got HI. What I notice here is H in front, so I know right off the bat, I'm gonna say acid. Right? Now, the second part of this, the more important part, obviously, is that hydrogen is partnered with just one nonmetal. It's not a polyatomic ion. So that means that this is a binary acid. There's only two elements present, hydrogen and iodine. So that's where we use the very specific name. We're going to say hydro. We're going to plug in IOD for the iodine. That's the root. And then we're going to add ick. So hydroiodic acid. So the IOD here is the root for the iodine, and the hydro is what's telling me it's just iodine. There's no polyatomic ion piece. If I compare that to the next one, I have HIO3. So I still have acid, right? As the second part, right? We always name hydrogen second by saying acid, which is what's weird. And now the IO3, that's my polyatomic. So before I can name this, I need to know what that's called. All right, so the IO3, that's my polyatomic. All right, IO3, if I look on my list, is called iodate. All right, now what do I do? All right, well, don't use hydro, because remember, hydro is what we use for binary acids. Instead, what I do here, right, I ate something icky, or I ate more and it made me sick. What I'm going to do is I'm going to change that ate ending, and I'm going to replace it with ick. So iodic acid. All right, so ate goes to ick, and then we add the word acid to say that there's hydrogen there. All right. So if you have multiple choice question and it says, okay, which one of these is bromic acid? The big thing you see is you've got HBr, which is binary, and you have HBrO3, which is non-binary. And we know that if it's HBr, it has to start with hydro because it's a nonmetal bromine with hydrogen. Just like we saw the nonmetal iodine with hydrogen, you always use hydro when it's binary. So HBr would be hydrobromic acid. The name here of bromic acid, because there's no hydro in front, we know that we're looking for a polyatomic, hydrogen with a polyatomic. So then it has to be the HBrO3. All right. H3PO3. Okay, so this is going to go back to something we were looking at just a little bit ago. We were using phosphate, but we can use phosphite, no problem. So we know PO3 -3 on our list is called phosphite. All right. If I have HPO3, now the charge has gone up by 1. So it's a -2 overall because hydrogen brings a +1. This would be called hydrogen phosphite. If I have, and that's what this is here, right? So I've added a hydrogen, PO3, still there. There's my phosphite. Charge went up by 1. So now it's a -2. So this is hydrogen with phosphite. If I added another hydrogen, the charge has gone up by 1, and I put a 4. I'm sorry. That's supposed to be a 3. Okay, we're talking about phosphite. Now, still phosphite, but now with 2 hydrogens in front, it would be dihydrogen phosphite. So logic would tell you that H3PO3 would be trihydrogen phosphite. And this is where it falls apart. I mean, I get it. I understand why they made this rule, but trihydrogen phosphite doesn't actually work. If we follow the strict rules of nomenclature, the difference is that saying hydrogen phosphite or dihydrogen phosphite, it still has the polyatomic ion name. So this is still a polyatomic ion. When I get to H3PO3, it's no longer a polyatomic ion because now the charge is neutralized. It's gone to 0. So now we have an acid, not a polyatomic ion. And that's when the name shifts. So we're not going to say trihydrogen phosphite. Instead, what we're going to do is say, okay, phosphite, like we did with the IO3, we need to change the ending. 8 goes to ick, or Sprite is delicious, ite goes to us. Now, there's a little catch because you would think, okay, well, this is just going to be phosphorus acid. Technically, it is phosphorus acid. All right, but we still change the ending. All right, the ite went to us. All right, and you can do OUS or you can do just US. I've seen both. Okay, so why did it bring back that extra syllable? And honestly, I wish I had a good explanation for you because I think it's again one of the little problems in the rules of nomenclature. The 2 elements that are problems are sulfur and phosphorus. It never made sense to me why sometimes the root for the nonmetal is just the phosp or the sulfite, phosphate. We just take that original first syllable. But then when we do acids, we bring in the extra syllable, the second syllable, and now that's the root. So it's only with sulfur and phosphorus that it becomes a problem. Phosphite becomes phosphorus. Phosphate becomes phosphoric. All right, I think acids ever include Roman numerals? Ooh, that's a good question. Acids will never have Roman numerals. Even though they are ionic, the reason why they don't ever need a Roman numeral is because hydrogen is always a +1. Now, the number of hydrogens can change depending on what it's partnered with. Like iodate is a -1. So we only need 1 hydrogen to balance. +1, -1 cancels out. PO3 is -3. So that's why we need 3 hydrogens to balance. But we would never need a Roman numeral here because hydrogen is always a 1. And really, that's the point of the Roman numeral is with those metals where the charge can fluctuate. But hydrogen's always a 1. So we don't need Roman numerals. Okay, so phosphite becomes phosphorus. Sulfite would become sulfurous. Those are just the two elements that are sort of the problem child. Everything else, not most, but everything else, it follows the rule. You literally drop ate, replace it with ick, or you drop ite, replace it with us. It's just the sulfur and the phosphorus that bring in the extra syllable. Okay, so next one, nitric acid. Again, I always felt like these are named backwards. Acid means I'm starting with H. That's my cation. Now, what do I notice about nitric? Well, I notice there's no hydro. So I know that we're not looking at just nitrogen, right? It's got to be a polyatomic. And ick would have come from ate because I ate more and it made me sick, or I ate something icky. So ick came from ate. So I know that this is hydrogen with nitrate. If I go and look at my list of polyatomic ions, nitrate is NO3 with a -1 charge. +1, -1 cancels out. So we would just have HNO3. All right. So now the rest of these are all kind of a mix. We're going to review everything that we've talked about, and this will be a great place for us to end our first session for today. So P2O5, remember when we were doing our flow chart, you always want to look at the first element to figure out where you are. All right. So P is phosphorus, right, from light bearer. And that is here. It's a non-metal. So what I think of is, okay, I got a non-metal in front. That tells me I need to use prefixes. All right. So not thinking any Roman numerals here, not worried about all the rules of acids. I'm just thinking prefixes. So 2 phosphorus, I'm going to say di, phosphorus. First element, name as is, add the proper prefix, so di for 2. And then for 5 oxygens, I'm going to go penta, and then oxide, IDE ending, always on binary compounds. So diphosphorus pentaoxide. When you have the double vowel, sometimes they'll drop the first one, and then this would just be pentoxide. Totally fine. All right, you pick, whatever's easier. Fe2O3. Now, again, look at your first element. We got iron, which we know is a metal. And then on top of it, it's a type 2 metal. So type 2, meaning we don't know the charge based on the periodic table position. So this is going to tell us our focus is going to be not prefixes, but we need the Roman numeral. All right, so everything has its system, right? So non-metal in front, think prefixes. Type 2 metal, think Roman numeral. So I need to think about my charges here. The only way to know iron is to know oxygen. So if it helps you to draw them out, you've got oxygen -2 3 times. I'm telling you, my brain and my hand are not talking to each other today. Okay, so I got oxygen -2, -2, -2. So overall, right, I have a -6 with those 3 oxygens. With the iron, I know I have 2 of those, and I must have a +6 because it has to cancel out the -6 of the 3 oxygens. So that means each iron here has to be a +3. That would get me to a +6 total. So what I'm going to say here is that this is iron, Roman numeral 3, and then oxygen becomes oxide. All right, so be careful because it would be so tempting to say di-iron trioxide, right? It looks like that would be fine. Paints a clear picture. Why not? Again, I didn't make the rules. Whoever made the rules said, you know what, we're going to name covalent compounds a certain way, and we're going to name ionic compounds a different way. And that'll be a way to clearly identify ionic from covalent. That's fine. Seems like it might overcomplicate it a little bit, but you know, we have to do what we got to do. So remember, you got the crisscross. Oxygen, -2. And the thing you want to check for is if the charge on the nonmetal, absolute value of 2, is the subscript for the metal, then the opposite will be true. So 2 is the charge on oxygen, which is the subscript for iron. So that means the subscript of 3 on the oxygen is going to be the charge on the iron. All right. But this first part has to be true. Like you have to know the charge on the nonmetal, and you have to see that as the subscript for the metal. And if you do, if that's working, then you're like, okay, good. I don't have to think about this too hard. That subscript's going to just be the charge on the metal. All right, so iron 3 oxide. if you had any chemistry where you had to know the classical name and you're like, well, wait, isn't that like ferric oxide? That's fine. I don't use the classical system. I think the stock system is so much easier. So if you had it in your past and you want to use it, go for it. But otherwise, just use the Roman numeral. I think it's easier. All right, Cri3. So chromium, okay, just like iron, it's another type 2 transition metal. So again, our focus is the Roman numeral. So we're going to say chromium. We're going to leave a space and come back because this is binary, iodine becomes iodide. Now, when I look at Cri3, iodine is a -1. All right, it's a group 7 halogen. Sorry, I should have probably showed you that. It's a halogen, always -1 charge, right, for that whole family as anions. So that charge of 1 on the iodide is technically the subscript for the chromium. We just don't write in ones, but that's technically there. So that means that that subscript on the iodine is going to be the charge on the chromium. So this is chromium 3 iodide. All right. Okay, couple of more here, a little smattering. Next group of 3. What I wanted to emphasize here is the importance of the last 3 letters. I know all of these are Pb, which is lead. All right, I had a student once say, I remember that symbol because peanut butter is like lead in my tummy or something like that. That's what she came up with. I always thought of plumum, which is the classical name, and I thought plumbing. And I don't know, that's how it stuck with me, but that may not be very helpful. So lead, remember, it's one of those metals. It's not a transition metal, but it's underneath the stair step. And we don't know the charge here. It can be a +2 or a +4. So those metals underneath the metalloid stair step are type 2s. We have to come up with the name, or sorry, the number. Just aluminum is always a 3. So if I look at NO3 on my list of polyatomic ions, NO3 is called nitrate and it's -1. Okay, so nitrate, that group is -1 and it's called nitrate. Now, what I look at again is the crisscross. The charge on the nitrate of a 1 is technically the subscript for the lead. It's just not written in because we don't write in 1 subscripts. So that means that the subscript outside the parentheses, right, not within the polyatomic ion, but outside the parentheses, that must be the charge on the lead. So this is lead, Roman numeral 4, nitrate. All right, 4 is a 1 in front of a V. If you like doing it the long way, go for it. I've got nitrate, 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 nitrate. I got 4 of those. So -4 total. Since there's only 1 lead to balance, it has to be a +4. Now the next one, what I notice is it looks pretty much the same. I still have 4 polyatomic ion groups. I still have the lead, but now the only thing that's different is I've changed the subscript of the nitrate from a 3 to a 2. And like we talked about, that means we've just dropped an oxygen, and that means we've changed 8 to ite. So this is lead 4, and then nitrate becomes nitrite. That's the only thing that's changed, is we dropped an oxygen, so we change the 8 to ite. 1 less oxygen gets the ite. All right, the last one here, what's changed now is it's binary. It's lead with just nitrogen, not a polyatomic, just nitrogen. So what changes here is the ending is now going to be IDE. All right, now if we think about the charge, right, we still need the Roman numeral. Nitrogen and the family that it is in, it is a -3 charge. All right, so nitrogen carries a -3. We got the crisscross working for us again. The charge on the nitrogen, the 3, is the subscript for the lead, which is a 3. So when that happens, then the opposite will be true. All right, so again, because we've got this piece working, the 3 and the 3, that tells us that the subscript on the nitrogen, which is a 4, is going to be the charge on the lead. So lead 4 nitride. So again, what I was trying to show you here is the importance of the last 3 letters, right? The only thing that's changed in the name is ate, ite, and ide. So the last 3 letters are really important when you're looking at naming compounds. or trying to pick one from a multiple choice question, the ending is really important, okay? So next three, I've got CS2. Again, always look at the first element. Carbon is a nonmetal. So again, we're thinking prefixes. So I'm going to say that I have one carbon, but since I only have one, I don't have to put mono. I just say carbon. And then I have two sulfurs. So disulf. And then again, this is where it's weird. In the acid, it'd be sulfuric or sulfurous. We'd bring in that extra syllable. But in the covalent and binary ionic compounds, it's just sulfide. We don't say sulfuride, we just say sulfide. So carbon disulfide, just like carbon dioxide. All right, Na2S. We have a type 1 metal. And what that means is we really don't have to worry about anything. We don't need a Roman numeral because it's always a +1 in this case. We don't use prefixes. So this one is, you just name it as is. So there's very little to do here. We just have to say sodium for Na, and sulfur becomes sulfide. So sodium sulfide. So whenever you start with the type 1 metal, the rule is no Roman numeral and no prefixes. All right, so when you start with a type 1 metal, to me, those were kind of some of the easier ones. So sodium sulfide, that's it, walk away. All right, Na2SO3, what's changed here is you still have your sodium. And again, you still don't need any Roman numeral or prefixes. But now, of course, this is non-binary. So we're looking at this SO3 group. And remember, if I can memorize sulfate, which is SO4, then SO3 is going to be sulfite. So again, kind of on purpose, last three letters. All I did here was change one letter, a D to a T, right? And I have a completely different compound, all right? So that's perfect timing, perfect place, what we're going to pick up with in the next segment. So back at 12:30, we're going to now start looking at some calculations. So we're done with the nomenclature part. We'll pick back up. I'll see you back here at 12:30. But otherwise, remember, use the second Zoom link. I think everybody's getting used to this, and I'll see you back in just a little bit.